All right, class, we're gonna get started. So welcome back from break. So today we're going to talk about ANOVA, which is essentially an extension or an expansion of our previous discussion of comparing two means. So we're gonna extend that to what we have to do when we have multiple samples and we want to compare the means of those multiple samples. Before we get into that, I just wanted to remind you all that there's a homework due this week, right? That was assigned before the break, so don't forget about that. And the next quiz will be a week from today. So it will be on Monday instead of Wednesday. A week from today will be quiz number 4, okay? Yeah, question. Quiz will include items that were covered on homework 6, right? So homework 6, I got out too late to make it a required part of your grade, but I still put it out there so you can look at it for practice, right? So I think the TAs have already graded the ones that were submitted. So the period to submit that homework and have the TAs look at it and give you the score you would have gotten had it been part of your grade, that period's closed. The homework's still out there for you to look at and practice. Yep. Other questions? Yeah. Let's talk about, so the question is, what lectures will this cover? Let's talk about that on Wednesday after I look at or start writing the quiz, okay, just to make sure. It's either going to be through lecture 11 or through lecture 12. So it would not include the Wednesday material, okay? But we covered a lot of material through lecture 11 from the previous quiz. So that's why I'm debating whether it will include today's lecture or not, that's all, okay? Other questions about the quiz? Or anything else? All right. Okay. So today we're going to talk about ANOVA, or analysis of variance. In previous lectures we talked about using the T statistic and the T test in order to compare the mean between two different samples. Right. So if we have sample A, sample B, and we want to know, is the mean of sample A significantly different than the mean of sample B? Then we use the T test and the T statistic. But it's often the case that we have multiple groups and we want to know if the mean values from multiple different groupings are different from one another. In this case, it's not, right? So you might think, well, if I have multiple groups, I can just do a bunch of pairwise comparisons using the T test. But if you do that, you end up being essentially overconfident in your estimate of there being differences between the groups. And so this idea of ANOVA that we use when we have 3 or more groups that we're trying to compare the means of is essentially a correction. We'll look at it as what it provides is essentially a correction on that overconfidence that would result if you just simply use the T test and compare it across multiple means. Does that make sense? A little bit of sense? And we'll see that more or less explicitly when we get down into the second part of this lecture. We'll see how one way to use ANOVA is actually just to modify the way that we do the T test to account for that overconfidence. But more or less, that's the fundamental idea, is that if we were to just apply a T test across all of our different means and make comparisons across all of our different samples, we would end up being overconfident in a difference between those groups. And so we use ANOVA when we have 3 or more means that we need to compare. And we're going to do this by going through a few examples, right? So the first example here has to do with whether or not batting performance is related to player position in Major League Baseball. And we have data from 327 players in a file, right, that we're going to load in. So it's noted here, right, we could do pairwise comparisons, but it's not as statistically correct. In fact, it's a little bit overconfident in differences if we were to just do a bunch of pairwise comparisons. So we're going to start with ANOVA. And the first thing that we're going to do when we're applying this ANOVA type analysis is we're going to evaluate the null hypothesis that all the means are equal. And so we're evaluating this alternative hypothesis that at least one of the means is different, right? So to start with, we're not going to postulate that one mean is different than any of the others. We're just going to start with the hypothesis, the null hypothesis, that all the means are equal, that there's no difference between the different samples, okay? We'll look at later, right? It's often the case that we might want to know exactly which one is different, right? If one of the values is different from the rest, we might want to actually say something about which, individual groupings. And we'll get to that in the second part of this lecture. But to start with, we're just going to do an ANOVA analysis of variance for evaluating the null hypothesis that all the means are equal to one another. So there's no difference between the means. So you'll see we'll be using results from stats models, or we'll be using library results or library code from stats models you'll see throughout this. And so we're importing that now at the top. This first test here, when we're evaluating whether or not these means are equal to one another from multiple different groups on a single statistic, this is called a one-way ANOVA, and so that's what we're doing here to start with. Yeah, so the question is, are they exact, or is the null hypothesis that they're exactly equal, they're equal within a standard error? The real statement of the null hypothesis is that they're equal to within our statistical significance, our specified statistical significance, right? So put it another way, it would be that based on the data, our null hypothesis is that based on the data, the means, in this case, the mean batting averages across our different fielder groups are statistically indistinguishable, okay? So now that's not the same as saying that they are exactly the same, right? And it's not even a statement that I know that they are the same, right? It's just that based on the data that I have, the null hypothesis is saying that based on the data that I have, I cannot distinguish among these groups, okay? That's our null hypothesis, to a specified level of significance. Okay, so that's our null hypothesis. And we're measuring batting performance using on-base percentage. Here we're reading our data into Pandas data frame, just to look at our data, right? So we have data for a number of different players based on their position, and we're really just looking at this column here, this on-base percentage column. One thing to note here is that we're simplifying this by replacing the 4 infielder positions with an IF label. So we're going to have all 4 of those things grouped together. And we can do that in data frames using this replace command. So in this case, we're replacing anything that matches one of these strings, right? First, second, third base, or shortstop with this label of IF. And so that now has changed. If you notice, Derek Jeter in there, instead of putting him as shortstop, we just label that as infielder. All right, so to start with, remember way back when, long before the break, something you've probably forgotten by now, but I'll remind you of, when we have a new data set, we always want to look at it, right? And we want to get a sense of what's in that data set. So we'll start with box plots in this case to display the data for each of the different fielder groups. And look at kind of the spread within that data and get some preliminary understanding of what we're looking at, right? And so in Pandas, again, one of the reasons to use Pandas is that it allows us to maybe simplify our syntax a little bit for making a box plot. So we're going to make a box plot of on-base percentage OBP, and we're going to group it by position, right? And this is what we have. Right, so we have on-base percentage versus position. So we have catcher, designated hitter, infielder, and outfielder. And from this, do we have any expectation about what we might see in this test? So remember, our null hypothesis is that there's no effect of position on on-base percentage, but does one of these look different from the others? Yeah, which one? Just anybody. DH, right? Designated hitter looks like it's a little bit higher. Might make sense, right? Designated hitter is a position where we have a player that's specifically just hitting, more or less. So it would make sense that this players in this position may have a higher on-base percentage, but we're going to start by evaluating the null hypothesis that these are all the same, and we'll go from there. So this definitely suggests that designated hitters have a significantly higher on-base percentage. But the question is that true at a significance level of 0.05, right? So are we statistically justified in making that statement, right? It looks like it might be true, but let's evaluate if we can actually justify that. There are multiple packages to do this. We're just going to do this kind of ANOVA analysis. We're going to be using just one here based on this Panda data frames. Later on, we're going to consider, so right now what we're doing is single factor ANOVA. So again, we're looking at just a single variable and for differences among the different groups in terms of that single variable. So differences among flare position in terms of just on base percentage. Later, we'll look at multi-factor ANOVA. And one reason we're using this package is we can use the same package for both. When we use this ANOVA LM, the syntax here is that we're saying we have to input a formula as our syntax. And so we're looking at on-base percentage as a function of position is what we're evaluating using our ANOVA test, right? So again, our null hypothesis is that on-base percentage is not a function of position, meaning our alternative hypothesis, the thing we're really trying to test here is whether or not on-base percentage is affected by position, okay? So that's our syntax. And so then we're going to essentially use that formula as our model. And we are going to build this AOV table using ANOVA LM. We're building this analysis of variance table, which is displayed here. All right, so this table is called an ANOVA table. And we're going to go through definitions of what all of these different terms are and how we estimate and compute these terms below. But one thing to look at here, just right off the bat in this corner of the table here, this PR that we have, PR greater than F, this is basically our p-value. So we've talked about p-values and how we compute p-values from a t-test, right, using the t-statistic. This is basically giving us the p-value that the position has an impact on the, in this case, the on-base percentage, the average value of the on-base percentage. And so just from this table, before we get into what all of these different terms are, again, we're going to do that just down below. We can see that this is telling us that our p-value is 0.115, meaning that we therefore cannot reject the null hypothesis at the significance level of 0.05. Okay, so even though it looked like there might be a difference between designated hitter and the rest of the positions in terms of on-base percentage, our analysis of variance is telling us that we cannot, in fact, at the significance level of 0.05, distinguish the means in on-base percentage from one another. So then what we'll see is that the governing statistic for this analysis of variance is now something called the F statistic. We'll look a little bit more at what that distribution looks like. But we can pull out the F statistic from this table as this AOV table.F. In this case, our F statistic is 1.99. And just like, right, so it's kind of analogous to what we did in the t-testing, right, our hypothesis testing about two means. We are going to be using the F statistic and the F distribution basically then to compute what our p-value is, right? So in some sense, the analysis of variance, again, is about computing a statistic. This time it's the F statistic that we then use to compute our p-value from the shape of that F statistic curve. In this case, our F statistic value is 1.99. So this table up here, though, also tells us some of the important values that we use to compute the F statistic based on our data. And these are the treatment sum of squares. So the important things here are the treatment sum of squares and the error sum of squares. So this treatment sum of squares is this AOV table sum squares, the first value in there, right? So index 0, and the sum of squared error, SSE sum of squares, is that second value, again shown in our table here as these two values for position and residual. Yep. Okay. What it's not showing us here, so other values that we need to know in order to evaluate the result are the treatment mean square and the error mean square, which in both cases require the degree of freedom. The F statistic is calculated as the treatment mean square over the error mean square, and the treatment mean square is defined as the sum of squared error for the treatments divided by the degrees freedom for the treatments. MSE is SSE over the degrees freedom for the overall condition. So in this case, again, if we go back up to our table, we can find that SSE is going to be this number divided by this number, and the treatment mean square is going to be this number divided by this number. Okay, so this table, and then our F statistic is that, just to make sure I get it right, that's mean square for the treatment over the mean squared error. So our 1.99, so here it's just confirming that it's, we can compute the F statistic from the other values in the table. Okay. But let's go down and look at what the, okay, so we can do some other analysis on how many players were in each position and plot what those are. That tells us how many observations we have overall, 327. But let's look at what those values actually are within ANOVA and talk a little bit more about how ANOVA works. So we just kind of went through an example of using the library in Python, right? Using this library within Python to compute ANOVA, get this ANOVA table. We gave names to some of the values in that table. We didn't talk about how those values are computed, so let's talk about that. And just a little bit more about what exactly we're doing when we do analysis of variance. So ANOVA is what we're doing when we're computing, when we're doing this analysis of variance, is we're comparing the variability of the group's means to the variability within the groups between the observations. So as an example here, so we have, let's say we have these three groups, right? 1, 2, 3. There is some variation in the means between these three groups, right? The mean of group 1 is not the same as the mean of group 2, is not the same as the mean of group 3. But that variation in the means is much, much less than the variation within each one of those groups. And so if we were to do ANOVA on this data shown here in blue and ask whether or not we can detect in a statistically significant way any difference between those means, right, we're likely to get back a result that no, we cannot distinguish between these means, because any variance between the means, like mean 1 looks a little bit low, the mean of group 1 looks a little bit lower, this one looks a little bit higher, this one's maybe down here. Any difference in those means is swamped by the variation within the groups. Okay. Whereas if we look over here in, if we're just comparing, let's say between 4, 5, and 6, groups 4, 5, and 6, there is some noted difference between the means. And because the variation within each of those groups is much smaller, we're much more likely to reject the null hypothesis and have our one-way ANOVA tell us that there is in fact a difference between the means of these groups. Does that make sense? So that's more or less the question that ANOVA is asking. It's, are the differences between the means of the groups distinguishable from the variance within the groups? Okay, so if we have large differences in means and small variance, then we're likely to reject the null hypothesis with ANOVA. If we have small differences in means and large variance, then we're likely to not be able to reject the null hypothesis. Right? We're likely to find that the means are indistinguishable. And what ANOVA does is it considers, and we'll see when we compute those different sum of squared errors and error for the treatment and all this kind of thing. What ANOVA is doing is it's considering both the differences within individual groups, as well as the differences between the means of those groups and the overall mean of the of all of the groups lumped together. So we're going to consider, kind of all of the different types of groupings together in computation of the F statistic for ANOVA. Yeah. Yeah. So what we're going to do is we're going to end up comparing. So one of the statistics will have to do with how the mean of each group compares to the overall mean, right? The mean of means. Another piece will look at how all of the values pooled together, how they compare to the overall mean. And by comparison of those two things, then we'll be able to compute this F statistic that then tells us about how significant or not these differences are. If that makes sense. I guess I didn't answer your question because there were a lot of things at play. So what we're doing with analysis of variance is, again, we're not asking a question of we're not yet asking the question of, is this one different than this one, right? That if we only had two groups, we would use the t-test and just compare, let's say, this group to this group. What we're doing instead is just asking, is there some grouping, right? It's one of these groups that has a mean that's different from the others. Okay, so we're kind of considering all of the variation together into these two statistics. The one that has to do with the treatments and the other that has to do with the overall error or the overall variance within the population. Okay. So maybe that gets an answer to your question, is that we're not yet considering any one individual mean. So we're looking at a sort of a summary of overall how the mean of each group compares to the overall variance within the population. Okay, so we can say that ANOVA simultaneously considers all of the groups, right? So we're not going to look at any one group individually. In this ANOVA, we're simultaneously looking at all of the groups, and we're going to look at whether the sample means differ from each other more than would be expected by random variability. Again, we're testing against the null hypothesis that all of the means are equal to one another. So if we look at, so let's look at some notation here. So we're going to have samples 1 through k. Again, for ANOVA, k should be 3 or larger, right? If k is 2, then we're just going to be doing a t-test. But so in ANOVA, so we're going to say the number of samples is k. Within each sample, we have observations that go from 1 to nk, right? So nk is the number of observations of sample k, right? So if we had 132 infielders in our data set, right, then and that was group number 3, right? So that was k is equal to 3. We had n sub 3, or n for infield, of 133. Right, so we have a certain number of observations. Each one of those sample groups has its own mean, right, which we're going to denote here as y bar sub k. And each group then has a sum of squares relative to that mean. Right, so the sum of each value minus the mean squared. So that's how we're going to get started. We have then Total sample size, we're going to use uppercase N for this. It's just the sum of all of the numbers, right, of observations within the different groups, right? So if there were, 10 designated hitters and 133 infielders and 10 outfielders, we end up with 153, right, as our total number of observations, just the sum of all the observations. And then we're going to have this overall mean or grand mean. You'll see it sometimes referred to as, is just the mean of all of the observations altogether. So we could do this by just taking the sum of all of the observations over the total number of observations. Or in this case, we can basically use a shortcut if we already know what the mean of each grouping is, that we can just take the sum of the number of values within each group times the mean of the group divided by the overall number of observations. Either way works to get the overall mean. So this is just the mean overall of every observation that we have. So then right, and then again, just remember, one of the goals of ANOVA is now to say whether the difference in our sample means, our y sub k, whether do those sample means differ significantly from this overall mean relative to the variance that's in the population, right? Relative to the variance that we see within the population. So another definition is that we have to look at is for the mean square. So when we say we have a mean square, it's going to be the sum of squares divided by the degrees of freedom that are appropriate for that sum of squares. And so we'll see that in analysis of variance, there are a couple of different mean square values that we're going to have to keep track of in order to compute the F statistic and then ultimately pull out our p-value for ANOVA. So in this case, the two mean squares that we need for ANOVA are the treatment mean square, right, which again was something that we computed from the values in the table, in the ANOVA table that we had up above, and the error mean square. So let's start with this treatment mean square. Okay, so if we look at this, so it's a sum over all of our groups of the number of observations within the group times the difference between the mean of that group and the overall mean or the grand mean squared, divided by the number of degrees of freedom, which is the number of groups minus 1 or k minus 1. So this treatment mean square is telling us something about how different the mean of each group is from the overall mean or the grand mean. Does that make sense? The grand mean, the overall mean of all of the observations. Right, so if we were to throw out this, remember this y bar, right, with no subscript, that's just if we were to throw out the sample labels and compute the mean of all of the observations, right? So we compute the overall mean of all of the on-base percentages that we observed, irrespective of which position the player was in, that's our y bar. And so this treatment mean square tells us something about how different the mean, let's say for each one of those sample positions, each one of those player positions was from the overall mean, right, if we ignored player position. And it's doing this in terms of a sum of squared error. It's weighted by the number of observations within each one of those groups. And the degrees of freedom here is just the number of groups that we have, k minus 1. So that's the treatment mean square. The error mean square, so remember the other side of this ANOVA. So in ANOVA, we're comparing how different the group means are from one another. That's captured here. We're comparing that to the variance that we observe within the data. And so that's what's captured down here in this error mean square, or MSE. So this is the sum over all of our treatments and all of the values within each one of those treatments of the difference between the individual observations and the treatment or the group mean, right? So in this case, it'd be the let's let's say we're looking at on-base percentage, right? So this would be on-base percentage, the difference between on-base percentage for each of the individual infielders from the infielder average on-base percentage. And the same thing for each one of those positions. We add all of that up to get that mean square error. And in this case, the number of degrees of freedom, the appropriate number of degrees of freedom here is the total number of observations, right, over all groups minus the number of groups, n minus k. So this tells us now difference again between the means versus the variation that we observed within each grouping in a big aggregate kind of way. And then our F statistic is the ratio of those two. Right, so our F statistic is telling us something about how large the difference is between the means of each grouping relative to the variation that we observed within each grouping, or the spread within each grouping. Okay, so if we had larger difference between the observed means of each grouping, the on-base percentage for designated hitters is really, really large relative to the overall average of over all our observations, right? That would increase our F statistic, increase our significance, decrease our p-value. Or if we had relatively low spread, right? This MSE is a measure of the spread that we observed within each group. If we had relatively low spread, that would also increase our F statistic or decrease our p-value, increase our confidence that there's a difference between the means. Okay, and that's fundamentally what we're doing with ANOVA. That makes some sense? Some sense. Yeah. Yep. So we haven't gotten to that yet. But we'll show what the F statistic is in just a second. Okay. Yeah. Good question though. Right. So that's just how we get the F statistic, and then the question is, what does the F distribution look like? So we use the F statistic with the F distribution to get our p-value. Okay. Just like we use the T statistic with the T distribution to get our t-value, let's get our p-value. Or we would use the Z statistic with the normal distribution to get a p-value if that's appropriate. Okay, so from this, we can see that if F is large, then we would say that there are large differences between the sample means and the null hypothesis would be rejected. So if F is large, a larger F tends to mean that we are more likely to reject the null hypothesis. So the F statistic is what we need to get the p-value. So now we need to define this distribution. And we're not going to go through a full derivation of what the F distribution is. We're just going to look at what it looks like, basically. But just know that we're using the F statistic with the F distribution to get the p-value, in this case, for our ANOVA. And now, in this case, for the F distribution, there are two important parameters that define what exactly the F distribution looks like. These are the k-1 and the n-k degrees of freedom. So those two values determine what the F statistic looks like. So just to take a step back, we introduce the normal distribution, which has a universal shape, right? It's just a bell curve. And if we're looking at, right, when we have a Z statistic, it's like a normalized, then we end up with a kind of a normalized normal distribution. And there is only one normal distribution. Right, we can scale it or move it based on what the value of mean and standard deviation are. But once we've normalized by mean and standard deviation, there's only one normal distribution. Right, there are no parameters defining the normal distribution. The T distribution, which we used to compare two means, was parameterized by the number of degrees of freedom. Right, so most commonly it was like something like n-1. If we were comparing a sample to the mean of a sample to a specific value, then our degrees of freedom was n-1 for the T statistic, right? And so we said T statistic was parameterized by degrees of freedom, right? One parameter. And if we change the degrees of freedom, we change the shape of that T statistic curve. So now we have F statistic. And F statistic, or the F distribution, is parameterized by two different degrees of freedom. And we can think of them as like the degrees of freedom for the differences between the means and the degrees of freedom for the variation within the sample groups. And it's just our degrees of freedom that we use in computing our mean squared errors. So k-1 and n-k. So here we have that defined as degree of freedom 1 is k minus 1. Degree of freedom 2 is that n minus k. And so for that set of parameter values, this is what our F distribution looks like. Yeah. K is the number of groups. That's correct. Yep. So let's go back up here to our degrees of freedom. So our first degree of freedom in the F statistic is the number of groups minus 1. So in this case, we had 4 different fielder groups, I believe. So our K is 3. Sorry, our K is 4, and our degree of freedom 1 is 3, right? And then our degree of freedom 2, this is what we use in that sum of squared error calculation, is the total number of observations minus the number of groups, right? So our, I don't know, 367 or whatever the number of observations was minus the number of groups, the 4 groups, gives us degree of freedom 2. Okay. And so those two things then parameterize the F distribution. Okay, so for those particular sets of degrees of freedom, this is what our F distribution looks like. If we were to plot this, different from the normal, different from the T, right? It's just a different distribution parameterized by those two values. And then when we're then, so earlier we then computed, so now let's see, we've computed the F statistic based on our values for the difference between the means and the variation within each group, right? The ratio of those two things gave us the F statistic. We then were able to compute the F distribution or plot the F distribution based on the degrees of freedom for the difference between our means and for the difference within our different sample groups. The 2 different degrees of freedom we use for F statistic, right? Give us this plot. And now we can combine those two things. And I'm just going to scroll up and look for what our F statistic was. I think it was just about 2. I just want to make sure that I don't confuse you all more. So our F statistic is just about 2. And so then our p-value is going to be the area under this F statistic curve greater than our F statistic number. So our F statistic value is 1.99, so it comes in just about here. And then our p-value in the F statistic, we always use the area underneath the upward tail or the right side tail. So our p-value would be the area under this curve or between this curve and 0 above that F statistic value of 1.99. And if we add up that whole area, that's where we get that 0.11 for the p-value. Okay. So a way of computing that is if we know the F statistic, we know degrees of freedom 1, right? That k minus 1. We know degrees of freedom 2, n minus k. We know that the CDF or cumulative density function, that tells us the area underneath the distribution up to that specified value. This is a valid PDF. Therefore, the area under this PDF, the total area is 1. And so the area underneath this curve from that point onwards, right, the right-hand side tail is just 1 minus that F statistic CDF. And that is our p-value. Okay. In this case, we end up with 0.115. Okay. Yes. This scale is going to be based on the number of degrees of freedom. This F statistic curve would change, would shift. Okay, and exactly how tight or narrow the distribution is will change based on that. Yeah. Okay. So again, now based on that p-value, which was larger than a significance level of 0.05, let's say we stated ahead of time, we want to determine, is there a difference between the mean on-base percentage for these different player groups to a significance level of 0.05? We'd say no, that's not true, right? Our p-value is 0.115. Therefore, the evidence is not strong enough to reject the null hypothesis. The data do not support the possibility that the average on-base percentage varies by player's field position. Okay, so even though the box plot looked like maybe DH had a higher on-base percentage, we cannot, based on this data set, we cannot support the conclusion that any of the means are different from one another. Okay. Okay, so there are some conditions that need to be met in order to do this ANOVA analysis. The first is that independence. So this means that all of our observations need to be independent from one another. So we just state this condition is generally met if the sample is randomly drawn and makes up less than 10% of the population. So we had 367 or something baseball players in our data set. That's actually don't know the total number of active baseball players or number of baseball players that could have been drawn from, but we'll say that's less than 10%. Because I assume this is over many years, not just over a single year. Another condition which we didn't check here, but is that the data that you're drawing from should be approximately normally distributed. We talked a little bit about normal probability plots and how you can use normal probability plots to assess whether or not a distribution is normal or whether or not data is normally distributed. There's a little bit more detail on that in the given reference, but for now, we'll just posit that the data that we analyzed was appropriate for ANOVA and therefore normally distributed. The other assumption that's important in order for us to be able to apply ANOVA is that of constant variance. So this is, remember, in the t-test, we had, when we were comparing between multiple samples, right, using a t-test to compare between multiple samples, we had different sets of expressions for whether or not the variances were approximately equal or not. In this case, we've only given the definition of one-way ANOVA, assuming that the variances are approximately equal between the different groups. So if we had one group that was had a significantly different variance than the other groups, then this formulation of ANOVA would not work. We'd have to use a different formulation, which we haven't defined here. Okay, just something to know for future application. Okay, so that's one-way ANOVA. Again, you'll get some practice on the upcoming homework. We're going to now look at how we can make statements about individual means within our samples, right? So, or differences between, let's say, individual player positions in this example. But any questions on this one-way ANOVA? So we're just looking at this null hypothesis of are all the means equal to one another? Okay, so so now we'll look at a different example using comparison of, let's say, midterm scores. And the setup here is that if the null hypothesis is rejected, then it may still be important to explore differences in the means, right? So had we rejected the null hypothesis in the baseball player example, we might then want to examine, can we indeed state that DHs have higher on-base percentage than other players, right? But we didn't even get that far. But let's say, but if we do have a case where we get that far, then we may want to explore differences in the means and say for which groupings are the differences statistically significant. And we can do this as well. And what we're going to do is then compare the means on each pair of groups. And so here we're going to have some data where we have exam scores from 3 statistics courses labeled A, B, and C. And we want to compare, so fundamentally what we're going to do here is compare A to B, A to C, and B to C, right? So we're going to do all the pairwise comparisons. And we're going to show that how we can do this analysis in 2 different ways. The first is going to be by essentially doing a t-test, but modifying the way that we do the t-test. So we're going to modify the t-test to account for the overconfidence that we would have if we were to just do the pairwise comparisons using the methods from the previous lecture. So that's going to be the first way. It's called the Bonferroni correction. And then we'll look at using the 2p honest significant difference method. So we're going to have the Bonferroni test and the 2p test, both different ways of making these pairwise comparisons between multiple means. And basically both answers to the thing that we started the lecture with was that if we have multiple groups, we have more than 2 groups. If we just use pairwise t-tests as we defined them previously, then we will end up being overconfident about any differences between the groups. So these are two different methods for essentially trying to account for that overconfidence. So our data here is on exam scores, again, between the groups A, B, and C. So this is what it looks like. The stats models routines require a slightly different format for this, so just something to watch out for as you're working with some data. We need to, in order for the stats models routines for ANOVA to work, we need to have all of our data values in a single column with another column that defines what the variable is. So this melt function actually can allow us to melt this data together in that way. And then we're going to replace the column names, right, for class, A, B, or C, and score of individual students within that class. Okay, so this is pandas. And so this is what it looks like. That's our head, that's our tail. We'll note that we have NaN values. We're going to have to take care of that later, but our initial results can handle, our initial code can handle those NaN values. So we have the proper format. We can go ahead with our analysis. Again, we're going to start by plotting it, see what it looks like. It's always a good idea. And this is what it looks like. All right. So again, we might expect that it looks like class C did better than class A or B. But right, we need to do better than just, it kind of looks like if you squint at it, we can kind of maybe see a difference, right? We want to put a number on that. We want to put a significance on that and do a test, right? Do a real test. So we're going to apply our general tool, right? The same tool that we applied earlier for doing ANOVA, or analysis of variance, right? So again, we're just evaluating against the null hypothesis that all of the means are equal. So we're not looking at the pairwise comparison yet. First, we're just seeing, are all the means equal? So we do our ANOVA and we end up with a p-value of 0.03, right? So this tells us that we can reject at a significance level of 0.05, we can reject the null hypothesis that all the means are equal, and that there is evidence at the significance level of 0.05 that at least one of the means is different from the rest of the group. So this doesn't tell us which, right? I mean, we can look at the box plot and maybe have suspicions, but this on its own doesn't tell us which mean is different. It just tells us that some of the means are different, and we're going to use this other analysis to go a little bit further. Yeah. So that depends. So again, remember the F statistic depends on the number of degrees of freedom, right? So what is large or small depends on the number of degrees of freedom. So I'd say the thing really to look at here is the p-value that we compute. And we would compute that p-value from the F statistic and the degrees of freedom. Does that make sense? Yeah. So there is no absolute number of what is a large F value or not. Yeah. Larger F value for a given set of degrees of freedom, right? Of these two sets of degrees of freedom, a larger F value would mean a lower p-value. But because the F distribution depends on both of these degrees of freedom, we can't say what is a threshold on this, right? So we set thresholds on this, on the p-value. Okay. But yeah, good question. So the differences in exam scores between the classes is not due to chance. So we have evidence that the difference is not due to chance. So now we want to make comparisons between the means of the different classes to see which one, right, which differences are significant. So again, it may seem reasonable to just perform comparisons between all possible pairs using the methods that we've already developed, the t-tests. The fundamental problem is that the tests are not independent of one another, and we will end up essentially overconfident in our estimate of any differences between those groups. And so there are different multiple comparison methods that have been developed to solve the problems. And again, the first one that we're going to look at is the Bonferroni method. So the Bonferroni method is basically like a modified t-test. So we're going to just change the essentially inputs to the same kind of formulas that we used to compute the t-test previously. So big difference here is that the significance level that we use in the t-test changes from alpha to this 2 alpha over k over the quantity k times k minus 1. So we're going to modify the significance level that we use in calculation of, in order to calculate our probability from the t statistic. And so this means that when we're looking things up using the t-table, so typically we were doing a two-tailed comparison. And so we would look up, so for a given significance level alpha, we would look up on the t-table or use the t-distribution for a significance level of alpha over 2, so we can capture both tails of the t-statistic. When we have multiple groups and we're using the Bonferroni method, so instead of alpha over 2, we use this value alpha over k times k minus 1. Okay. And we'll look at how that changes what we're looking up in this example. In this Bonferroni method, we'll often use confidence intervals and look to see if those confidence intervals overlap with our critical value to see if the differences are statistically significant. And the way we define those confidence intervals for a Bonferroni method is we look at the mean between group I, where the confidence interval is defined as the mean between our group I minus the mean between group J, plus or minus the t statistic that we calculate based on this modified significance level, times the square root of MSE, the mean sum of squared errors, times 1 over Ni plus 1 over Nj. So this MSE we can get from the ANOVA table. So just as we did before. So again, it's just given in that ANOVA table. It's already been computed for us when we did the ANOVA earlier. And so we end up with the MSE, again, is the sum of squared errors, SE, divided by the degrees of freedom for the N minus K within the population. So and again, that's all in the table for us. And so from that, we can compute 185.2. We can also use the same formulas we had up above for MSE. And then we're going to evaluate the t statistic at our specified significance level, including the number of comparisons. So again, we're going to use a significance level of 0.05. Right? That's the significance level at which we want to evaluate if there are differences in the means. Our number of groups is 3. Right, so our k is 3. And then, so the value that we're going to use to look up the t statistic is given as alpha over k times k minus 1. So alpha, so 0.05 divided by 3 times 2, right? So, or 0.05 divided by 6, which in this case gives us a value of 0.0083. So notice that this is lower or more stringent than the 0.0025 that we would have used if we were just applying a t-test comparing 2 samples, right? So this Bonferroni method is basically correcting for the overconfidence that we would have if we used just a standard t-test for comparison between these different means. So now using that, we can now find our t statistic, right? From, in this case, using the stats t ppf function for 1 minus this effective alpha, this modified alpha, based on the number of groups that we have, and the number of degrees of freedom, which in this case is our n minus k. And from that, we get a t statistic of 2.4. Now, we want to find what is the p-value that corresponds to this t statistic. We cannot say in absolute terms what is a big t-value or what is a small t-value, because the t statistic is parameterized by degrees of freedom. So we're going to look this up, right? Look up what our p-value is. Or so we could look up what our p-value is. Or in this case, we're going to use that t statistic to compute our margin of error. And we'll look at our confidence intervals on the differences between the different group means. And so that's what we're doing here. We're computing the difference between the individual pairs of samples. So this is like the difference between group A and group B, the difference between group A and group C, the difference between group B and group C. And then for each of those, we're then going to look at margin of error for those differences, for those pairwise differences. Right? So each of them we're going to evaluate using the formula we gave up above for those confidence intervals. I'm just going to scroll up. Right, so we're going to evaluate this for each pair, for each IJ pair, right, for A and B, all right, where it's A and B, for A and C, and so on. That's what we're doing here. And then we're displaying, then we're using that to compute a lower and an upper bound, right, 95% confidence interval on those differences between the means, right? So again, A to B, A to C, B to C. And so what we see is that the mean differences, right? So the means are not all the same. So there's the difference between all the different groupings, right? The different individual sets of means. But now if we look at, we use this margin of error that we computed using the t statistic, and we use that to look at what our confidence intervals are, 95% confidence intervals are. We can see that between A and B, right? Those are the two classes that look pretty similar to one another. Our confidence interval includes 0. So therefore, we cannot say to a significance level of greater than 0.05 that there was any difference between those two means, right? Because this interval overlaps with 0. So it doesn't look like there's any difference. There's no statistically significant difference between these two means. If we compare A to C, that was the second row, it also overlaps 0. So in this case, we cannot reject the null hypothesis that the two means A and C are equal to one another at a significance level of 0.05. And therefore, we cannot say that group A was different from group C based on this data. But if we look at our comparison of B and C, that's this third line here, this does not overlap with 0. So we can say to our significance level of 0.05 that the groups B and C are different, right? That statement is justified to a significance level of 0.05. Okay, that makes sense. That's how we'd use the Bonferroni test. So it's going to tell us the difference between those two groups. So ANOVA justified rejecting the null hypothesis that all the groups were the same, and we use this Bonferroni method to say that the actual difference was between group A and group C. Sorry, group B and group C. All right. The other way of doing this is with the Tukey honest significant difference method, which we're going to go over in just a couple of minutes. What I'll say for this one is that we're mainly using software to compute this Tukey method. So we do Bonferroni first because we can go through the formulas, see it as a correction of the T overconfidence problem, right? T distribution overconfidence problem. The Tukey method is mainly done in software, and honestly is the method that's most often used when we're making when we're doing these kinds of multiple comparisons. The Tukey method is a little bit more conservative, so it's a little bit less overconfident than even the Bonferroni method is. And so the Tukey method is the generally accepted method to use here. So the way we're going to do this, we're using this pairwise Tukey HSD function. Well, first we have to drop so one thing to note is that we can't have NaN values in the library that's used for evaluating Tukey methods. So we have to drop those out. And then we're going to, this is the function we use to run the Tukey HSD method. And what we end up with is a lot simpler than doing the Bonferroni method, doing all those T statistics calculation, although you could write code to do that for yourself. What we end up with is a table that looks very much like what we did for the Bonferroni method, where we basically just corrected the T statistic with a little bit more labeling, telling us the comparison between group A and B. This is the mean difference, right? The difference between the means of those groups. That's the same as what we had before. We'll start here. It's giving us the lower and the upper bounds, right? And again, we can see these are 95% confidence intervals. It overlaps 0. Therefore, we cannot reject the null hypothesis. Our p-value was greater than 0.05, right? We cannot reject the null hypothesis. For a comparison of group A and C, again, we see that the interval range overlaps 0. Therefore, our p-value is greater than 0.05, and we cannot reject the null hypothesis. Now, for comparison between B and C, we have a larger difference in means. The 95% confidence interval does not overlap 0. Therefore, our p-value is less than 0.05, and we can reject the null hypothesis and accept the alternative that there was a difference between groups B and C. Okay. So just some things to know here. This FWER, that's called the family-wise error rate, is basically the chosen significance level that was used to generate that last column there. Okay. And we can see that it gives us results that are similar, but if you look very closely, just a little bit more stringent than the Bonferroni method. So if we look at for example, the comparison between A and B, we have negative 9.19 to 2.9. Compare that to, actually in this case, it's slightly wider, but we have very similar values. We'll just say we have very similar results to what we had with the Bonferroni method. So for example, between B and C, we have a value closest to 0 of 0.7. And here we actually got a little bit closer to 0. Actually, in this case, I guess the Bonferroni method was a little bit more stringent. Sorry, in general, the Tukey method is a little bit less overconfident than the Bonferroni method, even though it wasn't in this example. And it is generally the accepted way of doing this kind of multiple comparisons. Okay. All right. Any questions on that before we get started? Before we, I guess, go to end the class. Okay. So on Wednesday, we're going to move on to lecture 13. We'll talk a little bit about the quiz. Again, the quiz is going to be a week from today on Monday this time. And you have homework due this week as well. All right. Thank you all.